We're going live to try to take a swing at this classical, the first 100 LeetCode problem. I'm going to share the screen. Minimum path sum. Share. Classic. Number 64, minimum path sum. So we are given a grid. I need a standing desk. Filled with non-negative numbers. Find a path from top left to bottom right, which minimizes the sum of all numbers along its path. Oh, gee, oh gosh, weighted paths. That reminds me of some special algorithms. I just remembered, yeah, those Dijkstra or whatever. I don't even know, algorithm. Oh yeah, so they're finding the shortest path between nodes in a weighted graph. Okay, that's between nodes in a weighted graph. But there's obviously weighted. Yeah, weighted. Is it weighted graph? Because I mean, in a weighted graph, what is a weighted graph? Okay. Weighted graph is where the edge has some weight. Is a graph in which a number, the weight, is assigned to the edge, not the node. In this case, we're talking about nodes, and their values. And we want to have the minimum path. So it could be, I wish I could draw here. I wish I could draw. Draw. Can I draw? Can I draw? Can I draw? No, I don't see drawing capability immediately. So, wait a second. Where is the timer? So, how big is the graph? Minimum. Mn is at least one. At least one. So my initial thoughts were, last time I just give it a quick glance. Can we, with the size of 200 by 200, so it's 4, do I know how much that is? 200 is 4. That's 40,000, right? Right, because it's gonna be 4 with, should be 40,000. Yeah, 4 zeros. And can we check out all the paths? Just go over all of the paths one by one. And calculate the sum. So like here, this path, and go over the path, the different step. And by the way, note you can only move either down or right at any point in time. And yeah, so right or down. The next could be like 1, 3, 5, 1, 1. And another one could be 1, 3, 5, 2, 1. then could be 1, 1, 5, 1, 1. And there is probably like, I don't know, something. Could be, I don't know, 10 or I don't know, 12 variations in this size. But there are going to be more when you get to 200. And the question was, can I go within the, good runtime limit? And today I asked myself, can I do it without going around each of them? And I'm not sure. My first thought is I cannot know the sum without checking all the paths. On the other hand, if we have a solution for some kind of path, either it could be part of the path, could be from the end to that spot, or from the beginning to this part, or to that number, or from the number to the end. But if we know the minimum and we saved it, the minimum path from that one, from that sub-problem, then when we get to it, we don't have to, when we get to it from another path, because we might be hitting, like this one is probably shorter path. Well, it doesn't have many variations from here, but let's say there were variations, and we could get to this one. We could get from different points. If the box was bigger, the grid was bigger. And by the way, it doesn't have to be a square. It could be rectangular, right? So, best solutions for sub-problems. Some kind of dynamic programming could be the way to go to avoid, because we don't have to redo. Like if we get to this one from here, and we know what's the minimum for this one, if we calculate the minimum path from this one, or from any point, then every time we hit it from the other direction, we don't have to, from all the other paths, we don't have to redo it. We will know the number in constant time, amortized constant time, amortized probably. If we store those in some kind of a map. But how could we do that? We could build those solutions along the path. We could. If we start from the end, one of the cool solutions, which works in many cases, you're going from the end. If we start from the end, and we create a solution for one, the minimum path, create a solution for 5. By the way, solution from 5 will use the solution from 1. We can do like go breadth first, search, for example, or we don't have to do breadth first. some kind of, way to start creating solutions for the smaller, shorter paths. So that when we get to that path, to that spot, we don't redo them. But let me explain why I'm thinking about it. Because I'm afraid that redoing them all, just resolving them as the new sub problem all the time, which is already suggesting, yeah, we'll do a lot of repetition, might run out of time. What is this error called? Runtime limit. Yeah, exceed the runtime limit. We could exceed the runtime limit, yeah. Because even this triangle of 200, which is 1, 2, 1, 2, 1, 2, this first half of this, if we take the worst case and we go, we take just half of that square of this 200 by 200, and like that, I guess, yeah. So if, let's say, it's 200 by 200, so it looks like every node has what? 2 options, going down or right, down or right. By the way, they do overlap, like every one overlaps. There is so many overlappings, but it's sort of like a tree, but it's not. So there is tons of overlapping, but it's still binary. We could avoid, we could just check one, okay, just one child, because we know when we check the 4, we'll check from the 3, we'll check 5. So it's actually I'm trying to calculate how many variations that will be. So that will be 1 plus 2 plus 3 plus 4, and that's till 200. These are the lengths of these rows, diagonals. We'll need to check. So 1, then we'll need to check 1 with 2. Oh no. Oh no, 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 no. No, we can't just check 135. We need to check 115 as well. Because it could be smaller, could be shorter. Yeah. So that means it's a binary tree. Sort of. Yeah, so it's not just that. That means, because every child has 2 nodes, and we need to check them. So as we go to the expanding path, it will be a binary tree of height 200. So it's like 2 to the power of 200, just that part. That's a big number. That's going to be, let me just tell you, 2 to the power of 10 is around 1,000. 2 to the power of 20 is around 1 million, I think. Right? Right? Am I right? Am I right? Calculator. I need my calculator. So we say 2 to the power of 10. Yes, that's about 1,000. Yeah, 1024. Yeah, but 2 to the power of 20. Yeah, that's about 1,000,000. And then if we say 2 to the power of 30, and that's 1,000,000,000. Yeah, so it adds, yeah, so it looks like it's too big. That's already 1,000,000,000. Yeah, here we already have 9. So that means 200, that's like 20 times that. So 20 times. Oh, so 10 is that, but that's like 20 times more. So 20 by 3 is like 60. It's like it's like 10 to the power of 60. Yeah, it's a lot. Much more than the system can do. I mean, not the system can do that, the runtime limit. Because 1 billion is 1 second, and we will be out of that. 1 billion is around 1 second, 1 billion operations. And we will need to check combinations. If my calculations are right, we'll need to check combinations before we get, just to get to the diagonal. 1 1 1 3 1 1 4 1 1 5 1 1 3. It's a depth first search with on a tree that has height of 200. Yeah. So that's a big number. That's a big number. Yeah, that's why we need dynamic programming here. What means dynamic programming? Dynamic. If I could spell dynamic programming, I could know is a technique of solving problems by breaking them down into smaller, more manageable subproblems. The goal is to find an optimal solution by combining the solutions to the subproblems. Yeah, if we could use some memory to know that the best solution for the best solution for 1 is 1. So the best solution for this, there's only 1. For 2, only 1. But for 5, we can check and see that for 5, the best solution is 1 1. And we can store that, and when we hit 5, we don't have to do that again. For 1, it's that. For 4, it's that. But we can't just find that solution and just build a path to this one, because that be such a not good better. The other path could be better. But if we start from the end and remember, let's say, yes, we've been doing it for like 20 minutes already. Just the logic and remembering some theory. Okay. I think we're getting to something. we are getting to something. If we store a map of subproblems, dynamic programming, DP is going to be make a map which will store arrays with 2 numbers. Yeah, which will store a map of arrays of integers of length 2. Pairs, yeah, those pairs, those coordinates, because we need both, right? We need both. And we will store the integer to that, yeah. So that's our dynamic programming. And we can start from the end and build the paths from the end to and do 1, we'll do 2, and then when we go in by diagonal and save that point, so we need to either go over that grid starting from the last. By the way, recursion could be also helpful here in some way, but I mean, to check this, to do the subproblems, I'm not sure we need recursion here. We just recursion will be if we know not sure we need recursion. Yeah, the simple way would be just to go diagonal, and at each point we'll do backtracking. Another term, backtracking algorithm means by recursively exploring all possible solutions to a problem, it starts by choosing an initial solution. Use brute force to find all solutions to a problem. Yeah, I think, well, backtracking is when we go track from the, it always looks like very backtracking. Yeah, geez, I mean, so many terms. But basically, yeah, we want to know about this diagonal. What are the best solutions? Because the next diagonal will be just based on that. It will be just like that. We'll just iterate over it, and we'll immediately know what is the best solution for that. What's the minimum path? What's the minimum path? Because, yeah, each one will check, and we'll have the map will just have it. Yeah, because 1 is already a solution and we know it. So when we go to 1, we'll just need an algorithm that, oh, by the way, we don't really need anything like much of a depth first search here, because we know where we can go. We need to just go one step lower or to the right if there is a way to go to the right. Adjacent, those adjacent nodes. Geez, that sounds, yeah, that way it looks like it's going to be a big O(n) solution, because we just will visit each value just once. we'll just use some memory. We'll use yeah, and yeah, linear memory and in linear time. Yay! I think we got it. I think we got it. Yeah, in the 25th minute. Can I do that in like 15 minutes? Oh, gee, or 10. I want to do it in 10 minutes. Oh gosh, I don't really need anything else. Yeah, I just need to start. I need some kind of loop that will start with the last one. Yeah, so I will be what do they call them? What do you call them? There is M and there is N. M. I mean, this is the first one is the number of the row. So I will be grid. The length of the grid -1. And J will be, should I call them I or column and row? Yeah, this is like row, this is column. I think row, column is a little bit more. Row, col is a little bit more intuitive. So now we start at the end. Okay. We start at the end. How do we go by diagonal? So next, so we start here. Well, we do need to stop. We need to stop where? So the next one will be a row. Yeah, that will be column -1, but on the last row. But that will be a different row. Yeah. Yeah. So there is a sub problem. We're looking at a sub problem. Traversing a grid by diagonals. Sub problem alert. Sub problem. How do we traverse it? By diagonals. And by the way, it's sort of the same as we'll be doing it backwards. Sort of the same. I mean, when we have that position, from that position, we need to check its children that are available within the boundaries. Yeah. Now, we'll have these children. Oh, gee, that's a breadth first search. Yeah, it sounds, yeah, we'll need to line them up, but we'll count from the end. And by the way, we could do that here as well. So to the top of the tree. To the top, it doesn't matter. I mean, we could solve from the top of the tree. Oh yeah, let's reverse. Let's start from 0, 0, 0. let's use a queue. A queue will be, the next nodes, and there will be a queue, a slice of slices, or actually we'll call them arrays of, we have to use here an array because map key cannot be, what do you call it, mutable? Oh, it has to be comparable. Yeah, comparable. You can compare arrays. Yeah, so let's do arrays also. In our queue as for the coordinates. So that will be a queue, and the first coordinate will be an array of 0 and 0. So for length of queue is more than 0, we will do our thing. Yeah, we'll know that. Okay, we'll remember how many. Yeah, so this the queue of jobs or nodes, this current node. So we need to remember that the level, we call them, can we call them row levels? In this case, there will be diagonal size. And by the way, we can really well predict their length. There will be but I mean, we can read them from queue, length of queue. So that's the diagonal size. And for that, for range diagonal size, because we'll need to check all those. And we will, it will change. It will start row, then it will start. We will get all the children of the current. So we will say, okay, now is Q0, and we'll work with now. To remember to save the solution for now, the minimum path for now, yeah. And that is another subproblem, yeah. And as we go over, we'll check the we'll put into the queue. So we'll enqueue the children of now, which is so if they exist. Okay, so if now 0. Okay, that's an array, so there will be now 0 and there will be now 1. Okay, and those are coordinates. Okay, so now 0. We need to check if it's within the boundaries. And if now 1 also needs to be checked. And if it does, that if it's within the boundaries, then we'll need to enqueue that next coordinate. So wait a second, now 1. So we'll have 0, which is 2. Now 1, so now 0 is within. We know that it's within. it's that specific. The now is within, but we want to check its left child and the right, or the bottom and the right. Let's do the bottom child. That will be now 0 minus 1. And that will be now 1. So a row, that was, this one was row, so we're going down. That one, the 1 is the column, and we need to move the column to the right, so plus 1. We need to make sure, so that's basically a number of row. And by the way, we can store that. We can store, yeah, let's store that. So rows is the number of rows. So it will be length of grid rows, and that will be length of grid 0. And so if that number because the rows will be also only going down, so only increasing, is less or equal to the rows. As long as that's fine. Because if it's not, we're not gonna check its children. So we have a right. Yeah, we have another child. We will enqueue it. So we'll have the. We'll say that now 0 minus 1, and now 1. So we have the child. That is a child that we want to enqueue. So that we're creating that array, and we say that Q is now append Q and that child. Now, same thing here. If it's less than columns, then Q append. Otherwise, yeah, because we don't want to, and Q append. Q an array of, by the way, what type of array? Integers. Integer array. Yeah, I was like, what am I missing here? It's the type, yeah, of the values. Now 0, now 1 plus 1. Yeah, so what am I doing? What am I missing? Why do I have this? Why do I have this? It's accidental. Okay, so we include the children, but I mean, we need to check the now. Now is the magical part. Yeah, so this, we include the children, and that's fine. Because the last value will like have no children, and we'll finish that. But we need to now we need to look up the tree, that graph. Well, sort of the tree. And we need to see if, yeah, the magical part is we need to use see if that value has any two parents basically, or two adjacent nodes upstream nodes. It's parents. Basically, there's many parents. Yeah, we need to check what their solution was. And by the way, we can set a solution for here. Let me let me say that map is that. And the first solution will be for this initial. I'm making this messy. Messy, yeah. Start. We know that start is that. Okay. So we'll have the start. And we'll know that the start is grid 0, 0, 0. So now we can see, okay, now we also need to check if in the other direction, yeah. If now 0, so if that row, if there is a row above, so, oh my goodness, I think I messed up here. Yeah, rows always grow. Columns, yeah, it goes down, it goes to the right, so they always grow. Oh, how could I do that? But in this case, we're going back. Yeah. Okay, is there a parent? Is there a subproblem we already solved? If now this one is more or equal 0, so if there is a solution above, then we're gonna check it. Then we're just gonna check it. If not, by the way, we only have to do that if now doesn't have already a solution, which in this case it does. But what if it's a 3 and there is no parent to there? We just don't care about it. There is no solution there, so we just check 1. 1 will not have any of that, so 1 will skip both. But it's already written, so it doesn't matter. All these children will be able to read it. So because I mean, yeah, if there is a parent above, then we say, okay, we need to check it. Like for 1, there will be above there will be a value in the grid. So, and in our dynamic program, in our DP, we will call for now -1, 90 -1. By the way, we need to check that not in the grid, but we need to check that in the DP, yeah. And in the DP, we need to build that now 1. Yeah, we need to build that array. Array of integer. Right? Right. So yeah, for this value, this array of integers, why I'm using this array? Why can't I use some other pair. What other pair could I use in Go? Time. What other pair could I use? For two numbers. Up to 200. It's just two numbers. It's a pair of two numbers. I could use a string of byte. So like what, string? Yeah. But I'll have to convert these coordinates into bytes and then a string of them, bytes. Let's stick to the integers, okay? Two integers, yeah. But we could use strings, yeah, for the keys for this map. We could use strings as well. Okay. So we have that key. Now that key, and this starts to look a little bit, I mean, I really want to simplify it, but you see, this is a key, or this is a node. And I want to check that in the map, in the P, we have this key, or we call it a node. Yeah, let's call it a node. And for this node, there is a value, and there will be a value. And that's our solution for the subproblem. And we just need to add that to our now in the grid. Now we'll go to the grid. Wait a minute. So no. We need to check the left and the right, and then pick the smaller one. Yeah, that's what we're gonna do. Yeah, so there will be like up is 0. Okay. So, oh no, not 0. I mean, if it exists, it's not the shortest path. What are the values? It's 200. Yeah. No, it could be its values, but the length could be much more. Well, the maximum length is 200 plus 200. Yeah, we could initialize it. So if up doesn't exist, if up doesn't exist, we don't want to compare it, but we will compare something. And for our DP now, right? We'll have the minimum between up and left. Okay, those parent subproblems, sub-solutions. Yeah, but I mean, yeah, the simple way right now is to say 200 by 200. Okay. I mean, there's probably a better way. So we'll say that. So if there is, then up is that. So whatever was in the P parent so dp parent plus what? Plus what's in the grid for now? 0 and now 1. And the same thing needs to happen for left. Yeah, so left is also maximum. Why do I put 200 by 200? If all the nodes on the path have 200 value, that's gonna be our like maximum. And it could be, but I mean, if it doesn't exist, if it will be that max. If the other one does exist and it has, so it will be still that, and that will be the answer. So that should work for that for now. So if now 1 minus 1 is more or equals 0, then also parent. So that will be the left parent. We'll have a parent. Initialize as a parent. So now 1 minus 1 now. Oh, wait a second. No, that will be 0. And 1 minus 1. Timing 51. Okay. Now, left is dp parent plus grid actually we don't need to do dp here. Hold the dp here. We just up is that it's wait a second. The grid, we don't need to do the grid. Yeah, repeat the grid. We can put the, yeah, we know the left, we know the right, and whatever the minimum, we just add the now to in the grid. Yeah. And so that's how we fill up the DP. And at the end, we'll know the last one. Yeah, in the DP, we'll have the last node. So we just need this slice. We'll say that and is in a slice array of 2 that is rows minus 1, calls minus 1, right? Yeah, I think that should be it. That should be it. Let's check the typos. Diagonal size is that, yeah, because we'll go for the diagonal size. Now, yeah, oops, oopsie daisy. Memory limit exceeded. I think we're doing something too much. Oh, wait a second. But so, wait a second. Memory limit exceeded. What could, we're building the DP is the only memory. Is that? So yeah, it's the memory that we're using. It will put, I might have forgotten something. So, okay. We'll go over the current diagonal. And, oh, gee, well, somebody has to take from the, somebody has to take deq. What about the deq operation? Q, yeah, somebody has to cut the Q. Out of index, well, who is out of index? Who is out of index? Okay, minimum left, right, DP now. It looks like the grid now 0, now 1. Now is an actual value. Index out of range with the range 3. Now 0. Yeah, so we're calling for some column and for some row. We took now from the oh, yeah, it has to be smaller. It has to be strictly smaller, yeah. Output, nice. At least we compiled and we got some numbers. Wow. Wow, we have 40,000, huh? We have 40,000. So DP is compiled by taking the minimum of the up and the minimum of the left. It looks like there are cases when both of them are not. Both of them are not. Oh, geez, there is no, yeah. The first one does it, yeah. Yeah, that's what I thought. There's something wrong with this specific situation. We need to know if there was a child or there wasn't. I was trying to do that, but with this, but yeah, there's a situation with both of them are not, and we get the 40,000. So up. Here it is, okay? We can say, why don't we say, by the way, values could be 0. Because what we want if that thing exists, if that parent exists, if that parent exists, if the upper and the lefter, if one of them doesn't exist, there is no other solution. Like for 3, there is only one sub-solution. It's 1. How do we handle that? Sub-problem. That sounds like a nice sub-problem. So we might get, there are several cases. One, we get only one of them. Okay, one, we have both, then we compare. Okay, if we have one of them, then we just assign it and we just use it. So if one is 0, yeah, I'm trying to think how to make it with like not without 100 of ifs. Just an optimal way to check that. Just an optimal way. This is an optimization. Yeah, if so there is a case if both exist, we have both numbers. What if it's a 0? It could be a 0. 0 could be a it could be a lot of zeros that lead, and it could be a viable solution, sub-solution. Yeah. So it still could be. I'm trying to. Oh, negative. Yeah. Why don't we put just initialize it as the negative? Well, then it will win in the min competition. And the mean competition, I won in the mean competition. Because, I mean, if there is only one value, you have to use it. Okay, you use that. So there are several cases. Let's just try them down. Yeah, so there is like up, there is just up, just left, and there is up and left. Okay, how do we check these? And yeah, we can do if for both, but then we'll repeat these calculations. If up exists, we check its solution up. If up exists. We're so close. We're this close. If left exists, we check its solution. If both exist, I mean, the easiest way, it feels like now, is to initialize it as negative numbers, and then we update our DP accordingly. Like if both exist, then we do that. Okay. So if up is more than 0, and left is more than 0, then that's our thing. Yeah, well, it looks like we're gonna have a case scenario here, like switch. We'll have a switch, and we'll have case, that case. In that case, we do that. We'll have another case. So if another case is up is more than 0, there might be like a super short, smart way to do that. I'm just not seeing it now. For now, if I could spell now, it's gonna be up. If you're gonna be dumb, you gotta be tough. Okay, DP now is left. Oh, I think I hope I have solved it like that. If you're gonna be undefined DP, okay, not DP. And by the way, we do need to add the grid to each of them, so we will do that afterwards. Yeah, so we'll pick, and then we just say DP now. We do need to add the current value to it. So that's how we, yeah. If you're gonna be dumb, you gotta be tough. Okay, it's still, oh, it's so close. It's just one value higher. Yeah, we're super close. So there is it looks like we calculated something twice. And I feel what could it be? Why? Yeah, what could it be that we calculated twice? The first value has already a solution. Oh, it looks like it's this first value, yeah. Because we will start, we will do it, we'll check its parents, and then we will add. What we will add? We'll add to the DP of it what is in the grid for it. No, we don't need to do that. And we don't need to do that. The DP of it needs to be, so that's start. We initialize start and we put the value to it as the value from the grid in our DP. I mean, I'm pretty sure we need to just say 0 here. We just need to say 0 here. It's probably gonna work. Yeah. But I mean, and when we actually do it, we will put the value in the grid. Yeah, we'll. Do we need to do dp at all then for this value? Because we're gonna put it in the. Are we gonna put it in dp after? dp now we'll do something with it. So we don't even need to initialize dp with it, because we will put something in it, right? So we don't really need that starting value at all, because we never check. Yeah, we don't really need that starting value. Let's do this make map, this beautiful map, the dp map. Baby, show me how this works with all the test cases. Time limit exceeded. Oh, it's still not perfect. Well, we did it. We tried. Okay, so we tried, and I think we're on the right path. I think might need some optimization, or there is an error. Why? Because it's kind of taking time limit. Yeah, I think there is some key thing we need to optimize, but I mean, when we check each parent, okay, parent exists, we just take its already available solution, right? Yeah, we calculate. Yeah, well, this is, so if parent exists, so this is the parent, this is its best solution. But by the way, the good news is I think we passed some good number of tests, so it's probably working, but it's just doing some duplicate work, right? So it checks both parents. Checks both parents. Where do we actually write? And we put the dp. So for the first one, it has no parents. It will just wait a minute, left. Jeez. Yeah, so all these cases will skip, and it will just add its own value. It doesn't have any. Yeah, we'll just add its value from the grid. Nothing was added. dp now up. Yeah, we didn't take anything from the parents in this case. We just have our value. But if we do, we'll take the minimum of them, or we'll take whatever is available. In most cases, it will be the minimum of 2 paths, and we'll write the dp with it. Could it be that the operations with this array are slow? I don't think so. But I mean, look, we only have we only go over the diagonal once. So we'll we'll add. I'm taking 5 more minutes. Okay. We'll add Otherwise, and I'll move it for tomorrow. Okay, if I, because I think we're close. To solving it. So we have the optimal solution. It's kind of immediate. It's constant time. We get the minimum, we'll write it. And the building of the next, as we queue, we get the now, we dequeue, so we clean the queue. But for each node in the queue, we add the available children. And by the way, we are creating duplicates because, I mean, this child will have two, with this one will have two children, but 3 will also has it as a child. So we actually, I mean, we do need to check both parents, but we don't have to add both children. That's the thing. Because, I mean, it's just gonna make it 400 instead of 200 max. But yeah, I think the children is where. So we need to take the left child if left child. So for this, we'll need to check the left, and at the end we just need to check the right. What I mean, if that thing is on top of the queue, we don't need to do that anymore. We need to add it, because this adds a lot. This just adds duplicates. That's could be. I don't think it should be time limit problem, but so basically, we only need to add the bottom child in the queue. And then we need by the way, they might not exist also, but I mean, if they exist, the bottom child and the left and the right child. The easy way, the stupid way would be to check if that it exists and it's not on top of the queue already, because the duplicate will be, so like this is valid, but this will be already on top of the queue. So in the queue, for that thing, length q minus 1, so that's top of the queue, is not that. So if the left one is not already there, yeah, we put it. By the way, time exceeded, use test case. Test cases. Wait a minute, what isn't it like? Out of range, minus 1. Oh, q, length of q minus 1. That's the last on the queue. Yes, so if the bottom, nobody put already the bottom one. That's the last on the queue. Length of queue -1. Why is it saying -1? Length of queue, it could be 0. Initially, the queue, okay, we take now. If it's 0, length of queue is 0, then -1. It's gonna be -1, yeah, but length of queue is 1, then the index is 0. So we can check that if the length of length of queue. If length of queue is more than 0, but I mean that's not the right check because so the bottom one is unconditional if it's the first one. Yeah, if there is nothing on the queue, then we put this thing. If there is something on the queue, then we check if it's not a duplicate, okay? So if we're within the boundaries and length of queue is 0, it's one case, or oh, but we need to be within the boundaries. So there is nothing on the queue. We go. We can't do that thing. We can't access the end of the queue. Why can't we access the end of the queue if it's empty? If there is something on the queue, then we check that. Okay, we can do 2 ifs here just to make it simple. Okay, if yeah, let's make 2 ifs. So if we are within boundaries, okay, then we also check so that's a general condition. We have to be within boundaries. By the way, if wait a second, if less than rows, yeah. So then we worry about it, okay? We don't have to worry if it's outside of boundaries. Now, if length of queues is 0, or it's not 0, but the current value is not there yet, then we do that. Yeah, I think like that could be working. Syntax, assignment, length of queue. Okay, let's check. Okay, that's not, we need a comparison. Undefined row, okay, rows, yeah. Wow, that's quite it's quite a challenging problem. 40 minutes wrong. Okay, we are way ahead when we're use test case. Wrong answer. Whoa, we're still one ahead. Oh, so we're on time. We're good on time. We just got a wrong answer. Wait a minute. Wait a minute. What could be wrong? So we still have one addition extra double burger. Double burger. Why? How did we get this double burger? So we're now skipping all the values that are already on the queue. So we're not creating duplicates on the queue. Could that mess up our algorithm? Because all the other tests passed. We passed all of the other tests. What this does is just adds to the queue only those that are not there yet. I'm not on top of it. Where is the double burger? DP now. DP starts empty now. And could it be... There is like 64 instead of 63. What could it be? Some kind of double burger. And in this case, we don't know. Is it pretty clean? Is it pretty clean? We add the current value from the grid to DP now. But DP now is minimum of its parents or any of the parent available. If parent is available, left, we have up and we have left. So if both of them are, we do that. If up is, we do that. Is left, we do that. And then we just add the current value in the grid of that current. We know that now is this node in the queue that we're looking at. So we checked its best paths above, and we added its own value. Right? Is that what we need to do? It's been working for us so far. Yeah, because so this was the best. So for 1, this was the best, and we just added 1, and that's the path. Yeah, I don't like that thing. I'm pretty sure we can improve on that, but it's just shortcut. And that means that the right is enqueued. Yeah, so the bottom So basically, the bottom the right one is include everywhere it's available. It's within the boundary. So this one is include, then this one, it checks, but it doesn't include the bottom. The right one is always added, but that doesn't change. That shouldn't be changing anything. That just queues up the node, and you will just do that node one more time if it's there. But it's not now. It's not now, and I mean, we can check if we are actually creating more than DPs than necessary. So that's cute. I think we've made a good progress with this. It's like almost 90 minutes. The good thing, we got the logic. We almost have the working solution. I think it's just one pass. Yeah, two tests to pass. I don't understand what's so weird about this test case. It just starts with a 0. Why? I mean, it should be working. Whatever is in the grid, we just get. We don't change the grid at all, right? We access the grid, read from the grid, but I think we'll call it a good attempt. Yeah, good attempt. We'll try to debug it tomorrow and maybe do some other problems. And we'll call it. Thank you for watching. Like and subscribe, and we'll see you in the next random LeetCode video.